Good afternoon, dear participants of the fourth Edge Computing Workshops. Edge Computing Workshop is a peer-reviewed international computer science workshop focusing on research, advanced and application of edge computing, a process of building a distributed system in which some application as well as computational and storage services. The goal of DOS is to bring together researchers and practitioners from academia and industry working on edge computing to share their ideas, discuss research works in progress, and identify new trends in this important emerging area. Okay, the main mistakes when submitting the article were inconsistency of the submitted works with the stem of the workshop and inconsistency between the content and the title of the article. The main language of the workshop is English. All accepted articles were independently reviewed and recommended for presentation of the workshop. So, 19 articles were submitted for consideration and 9 of which were accepted for presentation of the result during the workshop. Today the time are not easy in our country, there is a war, but we scientists do not stop and try to continue working. We are glad to welcome all of you in our workshop, so we wish everyone fruitful work and interesting discussion. And I invite to speak with Director for Scientific and Pedagogical Work, Andrei Morozov. Andrei Morozov, please.
Good afternoon, dear participants of the fourth Edge Computing Workshop. We are sincerely glad to welcome you to our event for the first time. After all, we are holding it despite any obstacles. COVID-19, the outbreak of war. We hope that the next year we will be able to meet you in person to our university for the workshop. I wish you all a constructive discussion and a peaceful sky. Thank you.
Thank you. And I want to tell you that our workshop will take place as follows. We will include a video recording of the author's presentation, and when the report is over, we invite all workshop participants to a discussion and questions. So, now we listen the first author. Our first author who presented main result of research is Victoria Smoley and Nathan Smoley, and his research is search and classification of objects in the zone of reservoirs and coastal zones. 1 second, please.
I don't think we are hearing anything.
Dear Tatiana, could you please share this video presentation using sound share? It seems to be any of us don't hear this presentation.
Hello, I'm Victoria Smoley. I'm from Kiev. I work in National University of Life and Environmental Science of Ukraine. Sergei Sayapin can be present since he is engaged in assembly and adjustment of drones. in territorial defense forces.
Hello, I'm Nathan Smolny, Technical University of Ukraine Igor Sikorsky Kyiv Polytechnic Institute, FICE student.
Search and classification of objects in zone of reservoirs and coastal zones. This presentation was made by Victoria Smolny, Nathan Smolny, Sergei Sayapin, and covers main parts of article search is classification of object in zone of reservoirs and coastal zones. In the modern world of robotics, many tasks require the intervention of artificial intelligence to increase the number of tasks to be solved, increase productivity, reduce execution time, scale processing, exclude a person from the processes of performing routine tasks, and ensure online information collection and processing routines. So, for example, creating maps and patrolling water bodies using traditional methods is a time consuming process that can be improved and accelerated with the help of artificial intelligence. In the modern period of development of unmanned aerial vehicles comes the realization that many tasks of research and observation can be transferred to automated drones, which will perform them faster and better due to the possibility of installing additional computing power as a payload. The subsystem will control the drone, which must move along the route at the point specified by the user and be able to detect such objects as boat, ships, buoys, garbage, islands, swimmers, and drowning people from the image from the camera. It was decided to use Ontalytic API combined with RubberFlow interfaces of data manipulation in order to set up the best possible working environment. Ontalytic's API provide well-documented train test environment with a lot of available model classes such as YOLO, SUN, YOLO-NAR, T-Data.
This slide tells us about data distribution. The largest number of markings belongs to the boat class, 1629 units. Along with this class, the following classes are well represented in descending order: swimmer, boat, and buoy, respectively 1498, 1270, and 1186 units. The garbage and drowning man classes contain the least number of images, which can lead to training anomalies. The distribution of images between datasets is shown on the slide. On this slide, you can see a model comparison performed by developers as well as our test results. According to the obtained results, we can see that the system detects objects on the water surface, but the classification of these objects is not that good. There are several reasons for this: errors in the leveling of the dataset, the small size of the dataset, and data source being not a drone but boat on the sea, so data source is not related to our targeted data source. On this slide, you can see the results of testing without classification function and lowered accuracy threshold due to models having a high probability of recognizing the objects boat and ship, but assign the recognized object to the wrong class, so misclassification problem takes place. Garbage objects were not recognized, but the boat object was completely ignored. So the lowering of accuracy threshold allowed us to get depicted results and so achieve desired output. Probability of finding objects on water surface is high, as well as probability of classifying water surface as any type of objects being low. A possible scenario of using the built model is the general collection of information about the reservoir without regard to the classification output. In the process of such exploration, I consider it expedient to collect a dataset that will correspond to the data from the drone. The data of the current dataset is data from surveillance cameras and video recordings from boats, as it was mentioned. In the future, form the dataset according to the developer requirements, applying the necessary data augmentation steps. And on this slide, you can see used sources.
For the interesting report, and we invite everyone to take part in the discussion. Who has questions for the speakers? Sergey Alexeyevich, please.
Thank you. A very interesting but too short video presentation. I have almost three questions. The first question, in the end of your talk, you mentioned you compiled the dataset from several sources, including images of boats, ships, biomes, garbage islands, swimmers, and drowned people. I see at last your slide these sources. Could you elaborate on the process of dataset curation and annotation, or you use them as is? The next question, how did you ensure the quality and diversity of your data sets, especially considering the challenges of labeling objects in aerial images over water bodies?
So, as it was mentioned, we collected a dataset from different sources. Then we proceed to labeling the dataset. It was all of this task was performed in a RoboFlow environment that provides all necessary tools like labeling and health analysis of dataset. The metrics of diversity were shown on the slides, as well as a spread over test, train, and validate datasets. So what can I add? The diversity. The diversity was a real problem since a lot of objects were so tiny that they were at least not visible, and so this may lead to like detection problems when the tidal wave or a bird may be classified as a ship. And so we decided not to mark so tiny objects. So we get the result that we have actually a low number of valuable objects marked. And so we decided to enlarge this number by implementing augmentation steps.
Thank you, Nathan. What the sources of augmentation? You use shifts or any other transformations, or you use an additional data which you get from scratch?
Well, we use dataset available. We use data available inside of these datasets, and so we applied resizing, stretching, and mirroring. Also, we decided to take a pieces with our needed objects and place it into other images, and so we acquire new image with different like context for neural network.
Many thanks you, Nathan. And no, and the last, my questions may be some complex. You compare the performance of two YOLO versions, versions 5 and version 8. Could you provide some insights into the specific characteristic or feature of this model that make them suitable or unsuitable for this application, especially in your case when the certain classes like drunk man, by show it that while both model correctly locale no other classes, they have low confidence in the predictions of drunk men and as you see, some birds above water bodies, etc.
So different. You want to know the differences in performance, yeah?
Yes.
And why they behave so. So well, we decided to use YOLO models due to our design decision. So we decided to implement a neural network on the board computer. And so we were limited in resources. YOLO models are destined to perform such tasks with the low amount of computational resources, and so we decided to use them. What's the difference between YOLO 5 and YOLO 8? Besides the differences in architecture, there is the lower number of neurons in YOLO 5. Indeed, this leads to more poor performance, but also reduces the computational power needed. Well, the difference in performance was not that significant, but accuracy between these two neural networks, well, was like 10 or 15%. So we decided to evaluate YOLO 8 and so continue with it and stick with it. What else? I want to mention that all of these disadvantages may be negotiated if you like take the neural network away from drone, place it on the ground station, and transfer video from drone to the ground station. In this case, we can set up a bigger and more difficult neural network since there is no need to stop it on drone, and we can set up it on the ground station. This may be the improvement step that can be taken.
Dear Nathan, dear Victoria, many thank you for the very valuable insights. Thank you.
Thank you. And we have one more question. So Valentin, you please.
Yeah, thank you very much. That was very insightful presentation. I have a question to the image quality. In fact, what images I have seen, they are very bright and very consistent and completely contrast. Quick question, what happens if you will be filming the fog or if you will have, for instance, very sunny weather with a lot of reflections? So how the network will behave in that case, and potentially whether you have taken any other measures like taken videos from different angles with different frequencies of cameras just to understand how you can indeed recognize the image.
So yes, we were quite limited with the images of the particular weather conditions. There were some foggy examples, but I guess it's not enough to completely avoid mistakes connected with the weather. As it was mentioned in the conclusion of my article, the system in its current state can be used to do this to do destined task and also gather information that may be used to make the new data set that will include all the required images from all weather conditions that may be possible. So indeed, on this stage, there will be a lot of mistakes during the foggy weather, the rainy weather, and so on.
Understood. Thank you very much.
Okay, thank you. Maybe someone want to ask the question? Okay, we thank you for your answer and your report, and we invite the next author to the speak is Andrei Rybko, and article Edge Computing Applications using aligner MEMS microphones arrive for UAV position detection, throat, sound, source localization. And now I will, 1 second, please. Okay. Share. We have some problem, Sergey Alexeyevich. Maybe you can.
1 minute. I'll start to share my screen and try to start this video presentation. 1 moment. Dear Tatiana, could you please enable me screen sharing?
Yes.
Using security setting.
Yes, 1 second. Yes, you can. Просто звуку нема напечатати. Presentation.
Може показати. Може, що спробувати?
Okay, we have authors of this presentation. Andrei Rybko.
I'm sorry, it seems to be this video without sound or else. we don't hear any sound in any environment. So I see it seems to be a good idea that Andrei can comment this video. Andrei, are you ready? I will start your video presentation, and you will be the leaf sound.
Може він онлайн доповідати? Не запис.
Thank you. I'm starting.
Yes, I understand. Thank you. But video was with sound. I don't know. Okay. Dear conference participants, microphone arrays have emerged as indispensable tools in a myriad of the applications, with one of the very primary applications being in the localization of UAVs, unmanned aerial vehicles, based on the sound of their engines. In this study, explores sound stripes in microphone array technology, with a particular focus on the development of linear microphone arrays utilizing MEMS microelectronic mechanical systems microphones. The discussion encompasses key aspects such as array efficiency, characteristics of MEMS microphones, comparison between analog digital MEMS microphones, signal processing techniques, simulation result, and avenues for future research. MEMS microphones have garnered considerable attention over their diminutive size, robustness against noise and vibration, and seamless integration into various devices. The structural and operational intricacies of MEMS microphones accumulate their advantages, such as enhanced functionality, environmental resilience, and ease of integration. These attributes position MEMS microphones as the preferred choice for microphone array application in diverse fields. A comparative analysis between analog and digital MEMS microphones unveils crucial considerations such as cost, yield, development complexity, and susceptibility to environmental factors. The argument in favor of digital MEMS microphones is compelling, citing their streamlined complexity, reduced susceptibility to electromagnetic interference, and expired production cycles as decisive advantages other analog counterparts. This comparison underscores the paradigm shift towards digital MEMS microphones in microphone array technology. The essay delves into the essential characteristics of MEMS microphones and compression, sensitivity, signal-to-noise ratio, dynamic range, and linearity. Furthermore, it elucidates the signal processing mechanism employed in MEMS microphones, including pulse density modulation, low-pass filtering, and signal conversion. These processes play a pivotal role in accurately converting sound waves into electrical signals with precision and ability, thereby enhancing the overall performance of microphone arrays. Efficiency is a pivotal factor in the performance of differential microphone arrays, especially concerning their behavior at varying frequencies. HD sharing light on how microphone instability impact array behavior, particularly at lower frequencies. Additionally, the role of weak equalization filters in mitigation with effects for low frequency enhancement is underscored. Different frequency ranges. Simulation and computational experiments of uniform linear arrays or omnidirectional MEMS microphones are conducted using MATLAB with parameters such as a microphone spacing and signal frequency being varied. The directional characteristics of these arrays are meticulously analyzed, showcasing and capability to achieve bidirectional patterns with specific geometrical arrangements. These results will promise for optimizing array designs tailored to specific application and environmental conditions. We conducted a simulation and computational experiment of a uniform linear array of two omnidirectional microphones with a MATLAB sensor array analyzer. The following model parameters were used. The distance between the microphone is 20 millimeters. The board has two MEMS microphones spaced 20 millimeters apart. This spacing is ideal for detection acoustic events. Additionally, the 20 millimeter spacing is equivalent to H millimeters, which makes it suitable of DIP, dual inline package. This is a type of housing for microcircuits, electronic modules, and some other electronic components. Experimentally, a distance of 0.017 match was determined for the formation of a bidirectional pattern. The resulting pattern has the shape of bidirection. As you can see, the design of the grail allows you to create a grail with the main rows direct at minus 90 or 90 degrees. To form a cardioid radiation pattern, as mentioned above, it is necessary to use delay and sum and filter and some algorithms. The meaning of these algorithms is what microphone signals and are added with different delays, aligning the phases of signals coming from the selected directions. Source localization for each frequency. In this case, the biomorphic algorithm makes it possible to amplify the signals generated by sound coming from the selected direction, i.e. performs a kind of focusing of sounds. ADMP 521 microphones were connected to the ADAO 1761 codec in accordance with the technical specification of both products. A model was also created based on an array of 4 omnidirectional microphones located at a distance of 20 millimeters. The following model parameters were used. The distance between the microphone is 70 millimeters. The speed of sound is 444 meters per second. The signal frequency is 10 kilohertz. So, during the computational experiment, we built 2 linear microphone arrays with bidirectionality. The directionality of these arrays can be easily converted to the unidirectional cardioid using now algorithms of hardware cortex. The tuning of the circuit to create cardioid directivity with the considered in further slides. Our SER concludes with a discussion on several pertinent questions and avenues for further exploration, including the dependence of array patterns of source frequency, the choice between analog and digital MEMS microphones, and the utilization of directional microphones. Additionally, considerations regarding the localization of moving sound sources, higher order differential beam array phones, and advanced signal processing algorithms are outlined. This discussion underscores the imperative for continued research for innovation to propel microphone array technology for new frontiers. In light of the advancement discussed, it becomes evident what the development of microphone array technology, particularly leveraging MEMS microphones, holds immense promise for a multitude of applications, including UAV localization. The convergence of innovative design methodologies, sophisticated signal processing algorithms, and the inherent advantages of MEMS technology has paved the way for unprecedented levels of precision, efficiency, and versatility of microphone array system. The study looks at setting up a microphone array to determine the position of UAV, unmanned aerial vehicle, based solely on the sound of its engines. The location of the microphone plays a crucial role to accurate localization. A mathematical model of pulse density modulation of a digital MEMS microphone is also considered. This work shows the dependence of the efficiency of differential array of first-order microphones on frequency. Based on the presented dependence of the directivity of frequency and the instability model of the microphone parameters, a rational operation frequency range for the normal functioning of the microphone array can be determined. In conclusion, the evolution of microphone array technology represents a convergence of innovation driven by advancements in MEMS technology, digitalization, and signal processing. By elucidating key concepts, presenting simulation results, and outlining future directions, this essay contributes to the ongoing discourse of optimizing microphone array performance and harnessing the full potential of MEMS microphones. As research continues to push the boundaries of innovation, microphone arrays are poised to play an increasingly pivotal role in a diverse array of applications ranging from UAV localization to smart environments and beyond.
Thank you for your interesting report, and we invite everyone to the discussion. Who want to ask the questions?
May I?
Yes, please.
Did you estimate what the accuracy of the location of the sound source does your method provide?
This study explores the use of the microphone array to determine the position of an unmanned aerial vehicle based solely on the sound of its engines. The accuracy of localization depends crucially on the arrangement of the microphones. The study also considers a mathematical model of pulse density modulation for a digital MEMS microphone. It demonstrates the frequency dependence of the efficiency of a differential array of first-order microphones. Based on these frequencies depends our directivity and the and stability model of the microphone parameters, a rational operation frequency range for the normal function of the microphones array can be established. And the study proposed a model of a linear microphones array based on MEMS omnidirectional microphones. With a specific geometrical arrangement, this array produces a bidirectional pattern, which can be easily transformed into a unidirectional pattern using isolated algorithms of hardware, ADAO 1761 cortex.
Okay, thank you. Valentin, please.
Yeah, thank you very much for presentation and for the report. In general, the question concerns the obstacles and potential noises. So how they potentially may impact your detection of the type of the engine and potential direction where it flies in.
Yes, I understand. Thank you for your question. I think our approach to utilizing MEMS microphones for UAV localization presents a paradigm shift in comparison to traditional methods. While conventional approach often rely on GPS or visual-based systems for localization, our method harnesses the power of MEMS microphone arrays to detect and analyze sound signatures emitted by UAV.
So mainly this is for detection, not for spotting and transitioning. Okay, thank you.
Yes, I understand. Thank you for the question.
Okay, thank you. Who wants to ask the question?
I have a question.
Nadia Mikhailina, please.
Thank you for your presentation, and I have one question. How does the integration of MEMS microphone arrays and change UAV localization compared to traditional methods? Thank you.
Yes, I understand. Thank you for the question. I think the utilization of MEMS microphone arrays revolutionizes UAV localization by offering unparalleled precision and adaptability. Unlike conventional approaches, which rely really solely on GPS or camera-based system, MEMS microphone arrays leverage sound propagation patterns to triangular UAV position with remarkable accuracy. We have studied a model of a linear microphone array based on MEMS omnidirectional microphones, which with a certain geometric arrangement give a bidirectional radiation pattern which allows for precision localization of UAV.
Thank you very much.
Okay, thank you. Who wants to ask the questions? Okay, no questions. We thank you for your answers. And now we invite the next author to speak is Natalia Kulikovska, Artur Timenko, Svetlana Grushko, and Vadim Shkarupilo, Automated Internet of Things System for monitoring indoor air quality. And I include the 1 second.
Good day, nice to meet you.
One second, please. I turn the video and
I am Artur Timenko. I am speaker of this presentation. Let's go. Automated Internet of Things system for monitoring indoor air quality. Natalia Kulikovskaya, Artur Timenko, Svetlana Grushko, Vadim Shkarupilo. The article explores the potential of Internet of Things technologies in creating a comprehensive air quality monitoring system with an emphasis on the indoor environment. The goal is to improve the quality of energy devices and protect the environment by ensuring optimal air conditions. This study highlights the role of embedded sensors in creating a universal Internet of Things based monitoring system that responds to various control parameters while excluding external data. It's proposed to create an information system for monitoring atmospheric air pollution based on the results of the analysis and selection of optimal solution of the complex technologies of the Internet of Things in accordance with the proposed structure of the system shown in Figure 1 using IoT technologies. Based on the structure of the system, three main modules were selected, namely the devices model, the data processing model, and the application model. Devices consist of a system control board, various sensors, auxiliary devices for emulating their operation, components for emulating the operation of a COM port for connecting external devices via the RS-232 interface. Processing models consist of certain instructions in the code which become valid sensor detection functions. Read data from the sensors, process them according to this function, and transfer them to the data visualization model for future display. Application model displays the received data from the sensors depending on their values with big circlet in a certain color. After receiving the data, if the values of the sensors are above the limits of the accept values, the system will notify the user about the action that must be taken in order not to put yourself and health the risk and improve the air quality. These models use the Blink IoT software application and it's built in functionality to visualize the received data from sensors in the real time. The proposed algorithm consists of 6 main steps, figure 2. Item first, formation of requests. Item second, subsequent processing of data in accordance with the secure section of the value. If the indicators are normal, data on the consumer sales in the component form to go to 6. Item 4, if the data indicators do not correspond to the safe path, the user will be sent an agreement with recommendation transition to item 5. Item 5, verification of changes in data indicators. Item 6, the user receives data from the sensor in conversion from the applications. The following indicators were selected for the air quality monitoring system. Air temperature can affect people's comfort and quality of life. It can also affect substance dissolved in the wind and their mobility. Air humidity can affect people's sense of comfort. Air with low levels of humidity can cause discomfort and negatively affect health and quality of life. High humidity can also promote the growth of fungi and mold. Carbon dioxide, CO2, elevate levels of carbon dioxide in the air can be harmful to human health, causing shortness to breath and other problems. They can also serve as an indicator of the decrease in air quality of the time. Dust particle PM2 and PM10. This particle is air can be very dangerous to health. They can penetrate deep into the respiratory tract and expand various lung and health diseases. Monitoring levels of the solution particle detects air pollution in time and takes necessary to prove it. Accurate measurements of local air quality limits is an aspect of ensuring a healthy and comfortable environment for living and working. This is especially relevant in major cities where people spend most of their time indoors. Measuring parameters such as CO2 concentration, humidity level, and air quality can identify your problems and help you take timely measures to solve them. It's worth nothing that Blink used to visualize data from the system's IoT sensor, as it allows receiving and displaying data in real time. A template was created after which a device was created which will receive, store, and display information from sensors. After that, a monitoring panel was created, which contains ranges of safe values for air quality parameters. Events were created that would be triggered if any indicators went out of the range of safe values. Figure 1. We also developed a system diagram, air quality analysis algorithm, and implement a monitoring system taking into account important parameters such as temperature, humidity, carbon dioxide content, and dust particles. The system reads data from sensors in real time and displays them on the monitoring panel, figure 2. When the values of any of the parameters you above or below the norm notification are sent to the message bar, which contain advice on how to improve the air quality, figure 3. It should be notated that system also provides a visualization with the help of a graph of all parameters and provides the ability to display by hours, days, and months, figure 3. Conclusions. The problem of air quality monitoring based on the automatic interaction of various devices that transmit data using the Internet of Things technology is considered. In the course of the work, the structure of the system and the method of data analysis and visualization, processing results using IoT technologies such as Proteus and Blink, as well as other tools we develop. Accurate measurement of the limits of indoor air quality criteria is an important aspect to ensure a healthy and comfortable environment for the operation of devices and work. Measurement of parameters such as CO2, concentration, humidity level, and air quality can identify potential problems and facilitate the adoption of time measure to solve them. A system analyzes the justification of the choice of software and technical solution which are necessary for the implementation of the system and all its stage we carried out. The use of technologies such as Arduino, Proteus, and Blink IoT made it possible to develop a real-time air quality monitoring system within the modern IoT concept. This developed system can be used as a prototype for organizing monitoring in changing environments and responding to various critical situations. That's all. Thanks you for your attention. Thank you.
Dear colleague,
I am Artur.
Okay, thank you. Thank you for your interesting report, and we invite everyone to take the part in the discussion. Everyone can ask a question in the chat. And now, who wants to ask the questions?
Yeah,
Yura,
I can.
please.
Hi, first of all, which IoT devices did you use, which sensors did you use, and where exactly which chip did you use for computing all this stuff? It was Arduino, it was Raspberry Pi, it was ESP32, or something else?
Thank you for your question. It was Arduino at first. It was ComPIM, its component which emulation comport to connect with interface RS232. DHT11, it's temperature and humidity. Then MQ135, it's to detect CO2. And potentiometer, it's for MQ135. And else DHT11, it's emulate date for PM2 and 5 and PM10. And plate Arduino Uno. And else software is Belink and Proteus, which in our science.
Yeah, I got you. And in this case, your device that you developed is more for home usage or for some factories or something else?
You may use this for home and for big structure, for example, factory, or but you must have also devices to connect in all big system.
Okay, in this case, did you need a stable internet connection? If you lost internet connection, did you store your data somewhere and transfer it to your database, for example? Or if you lost connection and if you lost the internet, the detection simply not working?
In this experiment, if you lost internet connection, it's disaster. You lost internet connection.
Yeah, and another question, do you research a security part of this application if you would use it for personal usage or for factories? Because it is important stuff if I want to use your device in a military factory, for example, and someone can connect to my server. It is possible to protect. Or it's just a POC and just a prototype.
Yes, I understand. In this work, it's not to use. Have only 2 people who have access on to this data, and I think it will be a new part of science in my next work.
Yeah, if this big stuff, yeah, I understand. And
Yes,
the last question from me, what for you is a normal situation? What for you is anomaly? And additional question from this, it is possible to detect multivariable anomaly, which is depends from 2 or 3 or more sensors. For example, if we, first of all, yeah, what is anomaly in your case? What is a normal situation? When the value is higher or lower as from normal, or you use some different techniques to detect?
In our work, it's you have a graphic indicator that you see, for example, if a temperature is 37, for example, degrees above 0, you will see in a web interface that it's red. If, for example, humidity will 42%, it will be good, and we see green color. And
it is that some worker should monitor the data, just monitor the graphics. You have some automatic detection.
Yes, automatic detection is automatic. Every some minutes, information screening from every from every DHT11 and transport to web interface, and you can and every who have access may see what now temperature or humidity on this object at all. And if any parameters are normal, then we have a signal from web interface or from chatbot, from Telegram bot that's made to add on to this project. And then we see alert temperature is very high, for example, and you must do something.
So in this case, you can set the parameters what is high temperature for our system. Yeah.
Temperature, humidity, and CO2.
Yeah, I mean that you just set the high parameter, and if our data increase this limit, we detect an anomaly and send an alert.
Yes, that's high or low.
Yeah. Okay, in this case, can we detect a multivariable anomaly when we, for example, have some correlations or some dependency between two sensors?
In this work, it's not to use.
Okay. Yeah, okay. I got you. Yeah, thank you.
Okay, thank you. And we have a question in the chat from Sergei Semerikov. Sergei Semerikov, maybe you ask your question?
Thank you, Tatiana Antonovna. A lot of questions was from your conference hall. No, my city is a city of PM100, which metallize your skin, broke your head, and carbonize your eyes. You saw that your system is, first of all, the monitoring system. We have a very large distance between even one districts in our city. No, for example, the city width is average 5 kilometers, but city height is no on all length is almost 100 kilometers. And in our city, it's the different districts, even in our meteorological compound, in different grid building, we have some a kind of a local weather. What about the combining the data from different locations, some predictions, etc.?
Maybe.
I'm sorry, a very long introduction. I'll be more clear, try to be more clear. In our city, we have places with a kind of local weather. We have hot weather, we have a wet weather. In place, no, for example, a radius 1 or 2 kilometers. What about the attempt to combine the data from different locations to make some predictions? Or your system only monitoring system what we can see in some location?
Thank you for the question. I understand. First of all, our system for indoor, maybe place one at factory in one part of country, second part of system maybe in another part of country in our city, and if system only monitoring and say alert if anything goes enough. And if temperature or humidity are high or low, and system say alert, alert, you must do something. I'm sent to you some messages. And human or people, man must to think what must to do to correct this humidity or temperature. I think that's it.
Oh, thank you. And my next question, I particularly in the chat something try to write. All we love, really love to invent the different bicycles, etc. But every our prototype in the end should be integrated in some production system. What about the seamless integration of your proposed system with existing build management system, or you think your bicycle will be quite unique and attractive for the end users?
I think first of all we use Blink software and Blink software and what else? And Proteus for simulator system. I think we maybe in our city may go to some factory and maybe to use our science for introduce in this in this part.
Valentin waiting for 10 minutes almost. Oh, sound, your sound.
Microphone,
We
Mr.
don't hear
Valentin,
you.
microphone. Put on.
Oh, yes. No,
Oh, do you
yes.
hear me?
Yes,
Yes,
yeah.
at
Sergey
last.
Alexeyevich, I was just meaning that if I would raise my hand physically, I will probably get tired. But no, that's not an issue. But I would say that it's very difficult to add something after Yuri, extensive set of questions and your questions. But I still have very small one. Artur, I didn't find the schema of your system, so probably that raised a lot of questions, and that's maybe a good moment if you will present the system in the future. Then it would be better for us all to understand how that's positioned and how that's interconnect with one another. My main question is that also touching the question of Sergey Alexeyevich, the question is that if you are not binding to parameters, then it's interesting to know how you are going to integrate with a second level system. For instance, if I know that the level of CO2 is high, then I can turn on the recuperation system. So then it automatically absorbs and take away all my CO2. In the same time, I don't know, maybe my humid level is already sufficient and all my wallpapers are very sensitive to it, how to bring it back. So the question still touches the question how these parameters correlate with one another in your system of taking decisions and connecting to the external system to grab some fresh air from the street indoor.
Thank you for the question. As you see, for example, if outdoor temperature will be 30 plus degrees, yes, of course, without conditioner indoor or anything what may temperature to below, this is used for
Conditioner.
help.
Okay.
Conditioner, yes, and we may physically correct parameters to put on conditioner, and temperature will be go to mean.
Understood.
And maybe, not maybe, I should in next our science projects we will be make to bet not better to big else parameters else the, some Arduino some temperature dатchik and what to introduce our science in practice.
Thank you very much.
Okay, thank you. Maybe someone want to ask the questions? Okay, we have no question, and now we invite the next author to speak. It's Arsen Petrosyan, and the topic test platform for simulation in hardware of an unmanned aerial vehicle on board computer. And I turn the video. 1 second, please.
Dear colleagues, we present a report on the test platform for simulation in hardware of unmanned aerial vehicle on board computer. My name is Arsen Petrosyan. I am a graduate student of the Department of Software Engineering of Zhytomyr Polytechnic. Designing and developing software for controlling UAV orientation in space takes a long time, including time for debugging, testing, and flight tests. Using classical methods of debugging and testing flight controller firmware is problematic. step-by-step debugging, generating messages to the console, using a logic analyzer, etc. Mistakes made in the development of UAV software can lead to emergencies or other unforeseen failures during operation. In this regard, the task of checking the reliability of the UAV's onboard computer software arises, which will simplify the maintenance, modernization, and optimization of the software. The purpose of the work is to develop a test platform for UAV using 3D virtual environment. To achieve the goal in the work, the following tasks must be solved. Analyze software testing approaches, development of the test platform structure, development of sensor and actuator simulator. According to the degree of code isolation, there are 4 levels of testing: unit testing, integration testing, system testing, and acceptance testing. However, we have software being developed not for a computer, but for an embedded system. An embedded system is a specialized computer system or computing device designed to perform a limited number of functions, often in real time. Embedded systems often need to work in interaction with the environment, using sensors to obtain input data, temperature, pressure, etc. And UAVs are no exception. The figure shows a simplified architecture of the UAV and its content. It can be seen that many different sensors are used as part of the UAV. Firmware is a software embedded in a hardware device, such as a calculator, GPS navigator, UAV flight controller, etc. The difficulty in testing UAV firmware is that the system is closed loop. You can see from the figure that it is not possible to stop the firmware from running, as the system will stop functioning. Obviously, a UAV is a complex hardware and software system, which creates difficulties in generating a complete set of sensor signals and the impossibility of creating emergency situations on a real UAV. To solve these problems, special software and hardware are used in the development, debugging, and testing of UAV firmware. One variant of testing UAV flight controller algorithms is to use a mechanical test platform with 3 degrees of freedom, rotation. It is also possible to move the platform with restrictions. The disadvantages of this option include the bulky platform. One of the effective methods of testing embedded systems is simulation modeling. Simulation modeling is a research method that uses models that describe real-world processes. Using such models, it is possible to test the real system without exposing it to danger. The simulation is performed using a virtual 3D environment. However, it should be borne in mind that 3D UAV simulators can be divided into 2 groups by functionality: simulators for training UAV operators, and simulators for developers to test and debug UAV flight controller algorithms. This slide shows screenshots of 2 of the most popular UAV flight training simulators. Most often, these simulators have good graphics and have the ability to connect a remote control UAV. This slide shows screenshots of simulators for UAV developers. Also, this first simulator is intended for operators, but due to the possibility of creating plugins for it, it can be referred to Universal Simulator. The second is a popular open source simulator for robotics. The firmware test in UAV simulation can be performed in 3 places: on a host computer using code compilation for the source platform, in an emulator on a host computer such as Camel, or on a real flight controller using cross-compilation of code for the target device. The first 2 variants are used when performing SEAL, software in the loop simulation. The latter variant can be used in HIL, means hardware in the loop, or SIG, means simulation in hardware simulation. This slide shows the structure of SEAL simulation. This slide shows the structure of HIL simulation. As we can see, the structures are similar. Only in the first case, firmware flashing is performed in software emulator, and in the second case, in real device. The main disadvantage of such variants of test system, like firmware modifications, are required, use of non-proprietary interfaces, and bulky system. Our work recommends the use of SIG simulation. In the first proposed SIG simulator architecture, using sensor and actuator simulator, This approach allows to eliminate the above-mentioned disadvantages. The main advantage of our approach is the ability to organize testing of any flight controller without having its source code. The sensor and actuator simulator performs the functions of real devices. The sensor and actuator simulator is configured similarly to its prototype, and the data registers are filled with information coming from a personal computer with a 3D environment. The software of the sensor and actuator simulator is implemented in the C++ programming language. For sensors with an I2C interface, the basis is an abstract class shown in the screen. To configure the sensor and actuator simulator, we developed a simple utility in the C++ programming language using the Qt framework. For each channel, the sensor model, interface, and variable address part, as well as the noise parameters are configured. Thanks everyone for attention.
Thank you. Thank you for your interesting report. And who wants to ask the questions? Valentin, please.
Is it good?
Yes, yes.
Thank you. So thank you very much for wonderful presentation. Yeah, I'm pleased because one compound work with a lot of like references and advantages of each method. My question was still touching the hardware part. So potentially what you presented is really noble and nice looking. The question is, how can I verify the change parameter definitely are tested in the physical model? So how that plays off. So for instance, if I do the change in your software, then how much time it takes until I check whether the drone is rotating appropriately with change frequency?
Thank you for your question. Basically, we can use any physical simulation behind the box. So our work is mostly about a hardware that knows how to simulate the different data, different sensors, and what is behind it is like a different story. We can use, for example, explain simulator behind it, which will actually take on its side any physics. So our box gonna like take data from the simulator, give it to flight controller in the needed format, and take output out of flight controller to explain simulator. So actually we can use any of it.
Understood. And the subsequent question, so you were using like C++ just for real test, but did you consider any transformation in any other programming languages? Because if we are speaking about the programming of the controllers, then variative part when you transition may definitely bring a lot of errors. Just in case if you consider that.
For Flash for hardware, software for hardware, we also considered Rust instead of C++, but we kept C++ just because it's just simpler.
Understood. Thank you very much.
Okay, who can also ask the questions? Sergei Mariko, please.
Thank you. I will try to continue the previous questions. Simulation in hardware is a classical approach to make your model is more smart. But the use of this approach for the testing drone firmware, we have some gaps between simulation and the real world operation. So the two questions. First questions, how scalable is this approach, particularly in accommodation the different types of drones and their associated hardware configurations, not only Mavics?
Yeah, thank you for your question. So actually, why this approach is the best is because you don't need to modify source code. You don't need to know the source code of the firmware. So you can test any flight controller. It could be loaded by Betaflight, iNow, ArduPilot. It could be even maybe Mavic if we know what's inside of it. I think that this is options that why we should use it actually. And in terms of scalability, I'm not sure that I completely got your question, but the idea behind it is that we use it for developers. So I, as a developer, want to add some feature to, for example, iNav, and I want to test it. I don't want to crash my drone. I don't want to, I don't know, drop something on my head. So this is why I need this testing system. So it's like scalability is not a feature here.
Thank you. Another field of the questions. Do you foresee any challenges or limitations in applying your methodology to drones with more complex system or mission requirements?
So the issue that might be here is that we need to simulate maybe different hardware. I forgot this word. So like when a motor started, for example, it might give some errors on the input of the sensors. And this is something that we can't actually like emulate. And this is why we tried to emulate it to add some noise, like, but it's not ideal real conditions.
Thank you, Arsen. And at last, the third questions, additional questions. What measures are in place to ensure that the simulation accurately represents real-world conditions, particularly in terms of sensor behavior and environmental factors?
Sorry, I'm not sure that I get your question. Yeah, can you repeat, please?
I'm sorry. We have some technical issues. So I try to write my question in the chat, and you will answer later.
Okay,
Thank you.
Okay, that's where we go next author, and we invite the Evgeny Voivodin and Inna Rozlony and his article Advanced Software Framework for Comparing Balancing Strategies in Container Orchestration System. And I turn the video.
Hello, my name is Evgeny Voivodin. I'm a PhD student at Bogdan Khmelnytsky National University of Cherkasy. My scientific research lies in the area of distributed systems, container orchestration systems in particular. In this presentation, I'd like to cover the software framework that I believe can be used to efficiently compare different resource balancing strategies in such systems. Let's dig in. Let's start with a definition of a container image and container. Container image is an application packed with all the dependencies that application needs. For example, imagine a Java application that, when compiled, becomes a set of binary files, bytecode. In order to run such applications, the one needs a Java virtual machine, which will be responsible for executing that bytecode. In such case, the container image would include both Java application and Java virtual machine of desired version. It might also include additional libraries and tools that are necessary for that application to function. Container, on the other hand, is an instance of container image. It consists of number of running processes, basically application processes, plus it has additional resources and limits associated with it. For instance, max random access memory it can use, ports assigned to it, etc. Having applications packed into container images opens a way to accelerate development of software products, since one can easily pack and transfer the whole application between servers and run those applications without additional requirements, and hence time wasted on managing proper versions of required software or fighting library compatibility issues. In big organizations, such approach also allows to easily use different technologies for developing applications. Containers quickly became widely adopted in the information technology industry. The microservices architecture, which often utilizes containers, became a standard approach to develop large and complex applications in a reliable and scalable way. The need to manage the lifecycle of hundreds or even thousands of containers led to the development of dedicated software, which is basically what container orchestration systems, such as Kubernetes, are. One of the key components that container orchestration systems include is scheduler. Scheduler makes a decision where the next container will be placed within the cluster of nodes, which are physical resources. This scheduling or balancing strategy is crucial as it might affect different properties of the application, for example, application fault tolerance or infrastructure cost. Recent works show the active development of new strategies, for example, utilizing machine learning techniques. However, there is no consistent approach and tooling to compare different strategies on a common basis. The key goal of this article is to provide a comprehensive design for an application capable of evaluating the performance of two or more scheduling strategies. In order to compare the strategies, there have to be metrics to use. The following metrics are suggested to be the basic ones that can be further extended if necessary. Utilization of cluster resources, or level of fragmentation, container deployment density, how many containers the strategy managed to pack basically, strategy request satisfaction ratio or acceptance rate, application fault tolerance, availability. Experiment is a key component that is configured to check the hypothesis among the given strategies. It consists of multiple parts, each of which must be separately configured and decided. Experiment is run in iterations. Before the first iteration starts, there is a setup phase, as illustrated in Figure B. The iteration setup includes the propagation of cluster topology to all the strategies. The topology essentially composes a set of nodes that have limits and can contain deployed containers. This topology is generated by the topology stream, a crucial first step. The topology stream allows for the definition of virtually any cluster structure, including the placement of nodes in physical racks for further fault tolerance testing. Additionally, the topology stream determines when the experiment stops, as it concludes when there are no more topologies to run the experiment for. The generated topology then serves as prototype for subsequent experiment iterations. The stream of configurations is responsible for generating container configuration or requirements to be placed within a cluster. Firstly, the stream can be either finite or infinite. An infinite stream will continue generating configurations as long as the packer demands it. Finite streams, on the other hand, can be used to test scheduling strategies for a very specific set of container configurations, to seek a better strategy or for strategy monitoring purposes. Regardless of whether a finite or infinite stream is used, virtually any sequence of containers can be provided, including random sequences. A crucial aspect is ensuring that the same sequence is fed to different strategies, where each strategy operates its own copy of the cluster to fill. Secondly, the stream can be used to define application families. For instance, it can generate several configurations that depend on each other and form a larger application, as commonly seen in microservices architecture. The specific implementation of the stream determines how to establish these dependencies, and the container configuration structure allows for such connections to be specified. Thirdly, the stream can replicate a single container configuration multiple times. For example, if an application must be deployed multiple times within a cluster to ensure better response to failures. Each aspect can be implemented as a separate stream representation. The decorator pattern can be employed to combine these implementations in a desired manner, allowing for a variety of system demands to be covered. The packer is responsible for making decisions regarding when to stop in case of an infinite stream of configurations. Such decisions are highly specific to the use case being tested. For instance, the packer might stop after encountering the first scheduling request error or once the cluster is full. While it is the packer's responsibility to execute scheduling algorithms, the packer itself does not depend on the specifics of the strategy implementation. After the packing process is completed, the results aggregator collects the packing results based on the state of cluster field by different strategies. Firstly, the aggregator's job is to collect important data points, which it does after the execution of every iteration. Secondly, it produces an aggregate that represents these data points. For example, the aggregator might count the number of containers deployed by each strategy and then compute the average number of containers deployed. The aggregation phase occurs after the last iteration for the current topology has been executed. The flexible interface of the results aggregator allows for the production of a wide range of statistical information. For instance, with all the data points collected, an aggregate might include percentile or median values. The aggregated results are stored within the experiment and get associated with the corresponding topology. One of the desired characteristics of a strategy is its management of the fault tolerance of the deployed system. The malfunction component assists in testing this aspect. It's important to describe the malfunction in combination with the malfunction results collector. This collector is similar to the previously described collector, with the primary difference being that it collects results twice, before and after the malfunction is introduced. This approach enables the malfunction results collector to compare changes resulting from the operation of the malfunction algorithm. For instance, it can assess how many applications or application families survived a network partition. The malfunction operates within the cluster, deliberately causing a distribution, disruption, such as removing a node from the cluster or reducing the percentage of available connections. A client-server architecture is a recommended choice for such an application. Firstly, the implementation of the previously described components is separate from the visualization of the experiment results. The system's flexible state allows for the choice of whether to represent such results with user interface components or whether another system should simply delegate the execution of experiments to this one while making decisions based on the experiment results. Another advantage of adopting a client-server architecture is the ability to have multiple server instances, thereby enabling high-level parallelization of experiment execution. Additionally, having multiple server instances enhances the overall resilience of the system. Here you can see a few results of the experiments run using software based on the design in the article. The experiment compares bin, pack, and spread strategy. It uses random configuration stream, and it stops when the first scheduling rejection occurs. So what you can see here is that average created containers is much higher for bin pack strategy over spread when such conditions are used. Here is another experiment that instead compares the fault tolerance of the strategy of the application using a particular strategy, and it also compares bin pack and spread strategies. And you can see that if after the packing the 20% of nodes are killed, while every container is represented by 2 instances, the spread strategy is much better tolerating application failure. So basically it means that in case of using spread strategy, at least one container survived such malfunction in 96% of times, while in case of bin packed, the value is much lower. The paper covers the design of the system that allows to compare different balancing strategies with flexibility being in its heart. The proposed division of responsibilities among different components such as topology stream, configuration stream, packer, strategy, cluster nodes, containers, aggregators, and malfunctions allows for extensive customization of the experiment flow to achieve the desired behavior. For example, such system can be used to compare the degree of resource fragmentation on the cluster nodes and thus assess the efficiency of resource utilization, measure the rates of containers creation or rejection, evaluate the availability of application encountering various network or node failures. Such system based on such design could significantly accelerate further research in the fields of resource distribution and distributed systems. The system would not only offer a platform for experimentation, but also become a valuable source of knowledge about scheduling algorithms. Hello, my name is Evgeny Voivodin.
Very interesting report, and we invite everyone to take a part in the discussion. Who wants ask the questions? Valentin, please.
Yeah, thank you very much, Evgen, for your report and for presentation itself. I have a quick question. So you mentioned streams of configurations, and my question is, if I have a cluster and I've seen that the configuration is like an input for you, so potentially in any cluster, any configuration of node you can create. What happens if I need to do a replacement of the configuration for specific node?
So there are two configurations mentioned. One is the topology of the cluster. It's when you specify how the cluster looks like. And there is stream of those topologies. For example, you might want to run an experiment on topologies of 10 or 50 nodes. And there are also configurations of containers, saying that there is a stream of things you want to balance within those nodes. And then yeah, so your question is regarding this topology of the cluster.
The later one. Basically, do you do two deployments or you do one deployment?
Yeah, so basically you define, the stream is pretty much an interface. You can say pretty much how it looks like it depends on what you want to test. For example, you can say it's random stream, or you can say that it consists of very specific types of configurations. So basically, that's a key idea of that. So this is a dynamic stream of things that you want to balance, and that's why this problem is actually is interesting one, because if it was that you would need to simply distribute a predefined set of resources within a cluster, it would be a completely different problem. But here you have a dynamic sequence of things you don't know about beforehand. So the strategy that I'm talking about has to make these decisions based on this dynamic stream of configurations. I'm not sure if it answers your questions, but please.
Not fully. It means that I would dynamically react to the environment. My still question was more rigid to the question that if I already had a node which failed and it had configuration A, and now I received a new stream to deploy instead of this node, and I need to do a replacement of the configuration in the same time. So that's why I ask about two deployments. But apparently, if you say that you are getting the stream as an income, that means it will just reflect what I give as a source.
Yeah, it will. If one node fails, for example, due to this malfunction components that I described, so we can randomly kill some nodes to see if our system is fault tolerant. We then and then a new node comes, then the strategy will make a decision within the scope of those nodes that are left. So the system itself doesn't prevent you from implementing the logic that will recover some node with different configuration, for example, and that might be actually a brilliant idea for extension. But in the way I described it, it's that the balancing strategy will have to make decision within the scope of existing nodes, the ones that remain available.
Thank you very much.
Okay, and we have a question in the chat from Sergei Samarikov. Sergei Alexeyevich, maybe you want to ask personal?
Communication with Valentin Nikolaevich was exciting and complete. It's fully confirmed with my questions. Thank you. No questions enough.
Thank you.
Okay, and Roman want to ask the question.
One question from me. It's very definitely interesting speech, and for me it's interesting something about dependencies. Did you look into dependencies between clusters of containers and configuration on it? Because it's the biggest problem of balancing when we have dependency between different clusters.
Yeah, so one of the things, to my understanding, the interesting thing about dependencies, in presentation, I call that application families. And basically, what you can do, you can say that here are 3 containers, and they depend on each other in different way. So you do that by specifying specific stream of configurations. And then you can say that container 1 depends on container 2 depends on container 3, or you can change that direction in any way. You can build pretty much any tree you want. So then you deploy that containers within the cluster and introduce some more function. For example, you say that 2 nodes cannot communicate, or 1 node is broken. And then we can see or check basically how many applications survived
that sort of malfunction. So imagine that we can check how many application families survive that sort of malfunction. Or what we can also do, we can say that every application family is deployed twice, meaning that every container will be there in having two instances. So that if one instance breaks, one instance still remains, right? So that we can say that application is still alive, it can function because that instance still remains available to the rest of the system. So that's one of the parts that I covered within that malfunction part, and basically that's what system can do, yes.
And another question in this configuration, did you do some pre-validation? Because if you do it as it, you will have a problem with circle dependencies. So if container A looks into container B, B on C, and C on A, in this case, it will be so hard to stop it. So you need to create some pre-validation if we discuss it about framework. Did you do it or not?
So there are two things. I actually showed two screenshots of basic web pages, which are not part of the article, but the paper describes the approach basically. So the paper itself is more about the concept of what can be implemented based on those components described. But the implementations that I'm currently working on is doing that. I don't remember, to be honest, I don't remember whether I checked that, but I think it can be easily done, and that's the main point of this flexible design. Yeah, thanks for the question.
Okay, thank you. And if we know questions, we now invite the next author to speak. It's Vladimir Artemchuk, Dmitro Shvaika, and Andriy Shvaika. And his article, Data Serialization Protocols in EIT Problems and the Solution Using SyncBoard platform as an example. And I will turn the video. 1 second, please.
Running processes, basically application processing.
Good afternoon, everyone. Today we delve into the critical role of data serialization protocols on the Internet of Things. Today's environment sees the rising popularity of the Internet of Things. Efficient data processing and transmission are now crucial for success in this landscape. Data serialization protocols play a critical role by facilitating information exchange among IoT devices. Widely used protocols like JSON, XML, and protocol buffers meet the demand for the fast communication. However, each protocol poses unique challenges for integration and scalability. Our research focuses on problems and solutions in IoT data serialization protocols. Specifically, we are investigating dynamic compilation of schemas in SyncBoard. Solving this issue is crucial for improving data management and adaptability. It will enhance performance in distributed environments, including edge computing. An ordinary device becomes an IoT device upon integration with an IoT platform. Standardized data formats are crucial at the application level, but their costs in IoT are often unclear. An evaluation compares JSON, XML, and PSON with commonly used protocol buffers. Benchmarking covers parameters like serialization, deserialization speed, binary file sizes, and encoding sizes. Protobuf leads data serialization for IoT with high efficiency in size and speed, broad language support, and extensibility. Formats like PSON show potential benefits, but protobufs continue to dominate in various IoT applications confirms its importance. Integrating devices with protocol buffers in IoT platform is a widespread challenge, not restricted to any particular platform. For our research, we opted to use SyncBoard as our primary tool. Founded in 2016 by Ukrainian programmers, SyncBoard offers an open-source framework with extensive features, making it ideal for in-depth exploration of challenges and solutions. ThingsBoard is fully open source IoT platform designed for data collection, processing, visualization, and device management. At ThingsBoard, we are using JSON formats for external communication because of their user-friendly nature, while protocol buffers are employed for exchanging data between components of a platform. The decision helps optimize. These decisions helps optimize the processing of large volumes of data while ensuring system performance. Device integration over protobuf in IoT platforms is a growing interest in using it directly at device level to increase efficiency and reduce network load. However, integrating devices with protocol buffers create challenges for open source platforms like ThingsBoard and others. The static nature of protobuf requires manually defining and compiling the schema for each new device type, hindering the platform's versatility and scalability, especially in cloud deployments. Integrating new protobuf compatible devices is time-consuming and error-prone task. An example of this problem is the integration of Fento devices into a ThingsBoard. Each change to the device on the Fento side requires recompilation of the system, necessitating constant support from the platform side. This, in turn, compromises the platform status as fully open source. The static nature of protobuf poses a significant challenge. .proto files must be precompiled using protobuf compiler. This generates source code in various programming languages, and any changes to the schema require a cumbersome cycle of recompilation and redistribution. This hinders rapid adaptation in dynamic IoT ecosystems. To address this challenge, we propose a software tool which enable real-time compilation of user-uploaded protobuf schemas. This allows dynamic interpretation without system downtime or complete code-based recompilation. Integrated into the ThingsBoard platform through device profiles, each schema represents a distinct device communication plan. Upon device authentication, the associated profile determines the relevant schema for message interpretation. This significantly reduces network traffic by transmitting data in compact protobuf format. Translation into a JSON-like format only occurs when necessary for user interaction or specific system functions. This approach facilitates rapid deployment of new IoT devices with minimal manual inversion or downtime. It marks a significant stride toward an adaptive IoT platform amid the sector's rapid growth. So, hence, this article examines the changing landscape of data serialization protocols in the IoT. We focused on the dynamic schema compilation feature in ThingsBoard. Despite its efficiency, protobuf suffers from static schema compilation problems, which limit the adaptability of the device. User-controlled real-time schema compilation can significantly improve the flexibility, scalability, and overall performance of an IoT platform. This ensures a smooth integration of new devices into the IoT sector. Research on the impact of real-time compilation will continue, specifically investigating the impact on latency reduction, bandwidth optimization, and overall system responsiveness in edge computing scenarios. Thank you. Thank you for attention. If you have any questions or comments, please ask them. I hope for further cooperation, and thank you again.
Okay, we thank you for interesting report and whoever questions, Vira?
Yeah, I have. I build in almost the similar stuff that things work, and my question is how to connect. For example, I have a batch of some monitors. How I can connect to things work? How this API works? Should I install?
Sorry, excuse me. You said you have a batch of what? Sorry,
For example, I
batch.
have some IoT device. How I can connect to?
Yeah, for such. So this is basically can be done by using. So we have a separate tool that call it ThingsBoard IoT Gateway, and it can be used to like transmit data from multiple sensors as from one device. But this required always the devices should be adaptable to use ThingsBoard specific format.
So, and can
And
I
yeah.
set up my database, for example, to store these values from my sensors, for example? Can I configure it into
In the ThingsBoard, so we have an ability to use the custom tables, but in usual way, our existing uh, tables that we're using in our open source database structure is usually enough because we're using key value pairs structures, and it's really there is only a few scenarios that I know where we're using a custom tables, especially for telemetry data.
And my last question, what capacity of is transferring data from sensor to the things board? Because when, for example, I want to monitor in real time some sensor and I send in for MQTT pattern, for example, I'm sending a data 1 point per second, for example. Can I visually see these changes second by second? What the capacity from transferring data from sensor to things board?
So this is really depends on both hardware and hardware side, and also in the way how the things board is installed, because it supports as a microservice architecture. Sorry, by default it's a monolith architecture, but it's also support a microservice architecture, and it means that you can set up as many transports for data transmission as you need. So it really depends on your needs, but I know that like we can. I know the scenarios where we're connecting devices that transmitting data with a very high rate, even less than second. In case, but this usually happens in case of some, for example, in there might be example when the system was stopped because of maintenance update, and devices collecting a lot of data on the background. They have some probably the devices have some also data storage where they can save the messages that are not acknowledged by a platform, and when the system is back online, the devices start pushing data, and the rate is very high in this case. But one key things of how we processing the data is that we're using different type of management, basically a stream applications like Kafka, for example, and we're using it for like data storage. I mean, for like a message queue, basically, not a data storage. Sorry, and if the device sends data even with some timestamps predefined. So we can, there might be some latency in the data processing, but it's also really depends on the software and hardware specifications. But we can guarantee that data will be processed because it will be still persisted in a Kafka, for example, until it will be not acknowledged by our system. So
Thank you. And we have a question from Valentin Minchuk. Valentin, please.
good morning.
This is
Good
a very
afternoon.
simple. Good afternoon. This is a very simple and very short question. So actually, you made a comparison, which is quite interesting. So what is the merit for switching to protobuf from JSON or from XML? Because for now we still stick to a lot to JSON. So can you recommend when it is better to switch to protobuf from JSON?
It depends on a use case in specific use cases, but really if so I basically do a basic comparison about how the size of a messages that are in a protobuf and the size of the messages that are in JSON. It's understandable that the protobuf will be have a like smaller size than in a JSON, and really it depends on communications that use devices. So if they're using LTE, like using just internet connection, so in some cases sending data to a like they are paying for each message, but this really depends on the device. And in cases where it's paying for each message, it's real taking a lot of costs. So I mean paying for message sizes. So if the size is when the size is smaller, then they are just paying for that, not a lot. So
Yeah, understood. My question actually originated from the fact that we have a lot of supermarkets which are using currently the IoT price tags next to their goods and stuff, and usually they are updating it. And I was pretty surprised that it's still using JSON, even though they are using internal network and could use something way speeder and I mean way better. Thank you, anyways, for the answer.
yeah, thank you too. Thank you for your question.
And maybe someone want to ask questions? So we have no question, and now we invite the next person to speak. It's Evgenia Andreeva, and the topic wireless technologies in IoT projects with distributed computing. And I turn the video. 1 second, please.
Okay.
The topic I'd like to share with you at our today's workshop is the wireless technologies in IoT projects with distributed computing. Nowadays, a large number of projects are based on the use of the Internet of Things. To make it simpler to comprehend, I'll use the abbreviation IoT from now on. When it comes to creating projects based on the use of the IoT, wireless sensor networks are often used. The purpose of our work was to analyze possible options for wireless data transmission in the implementation of IoT projects, both in edge and cloud computing, as well as the practical determination of the range of sensor data transmission between microcontrollers for each proposed option. A short-range wireless sensor network uses edge computing to display information within the reach of edge devices. So, when implementing the project of a home weather station, it is not necessary to require access to the global network. The transmission of temperature and humidity measurement data can be carried out using communication protocols of wireless sensor networks over a short distance. We developed a project of a home weather station using an ESP32 microcontroller and a DHT11 sensor. The results of this project are right now shown on the screen. Data transmission of temperature and humidity measurements was carried out by the Bluetooth interface with display on the mobile device in the serial Bluetooth terminal application. I'd like to point out that the maximum range of communication between devices in the room was up to 30 meters. As said before, a home automation system of any standard can work completely locally without access to the internet, which eliminates delays in the response of smart devices to events. The project of a home weather station was implemented using Bluetooth without access to the internet. Here is another example of a project that can work completely locally using ESP-NOW technology. This technology, developed by Espressif System, can also be used for two-way forwarding of data packets between controllers. It is based on a simplified Wi-Fi protocol. The results of distance measurement transmission between ESP32 controllers using ESP-NOW technology right now shown on the screen. The distance was measured by an ultrasonic sensor. The distance itself was calculated in centimeters on the edge device. Received data was displayed on the laptop screen. During the practical implementation of the project, it was determined that the range of data transmission is up to 100 meters. When it comes to implementing projects not only locally, there is a need to have an access to the internet, of course. Transmission of sensor data to a server, cloud service, or edge user can be done through a gateway. This approach we use to implement indoor air quality control project. Measurement data from indoor air quality control sensors were transferred to a gateway using NRF24 LO1 transceivers. A DHT11 digital sensor was used to measure temperature and humidity. An MQ2 analog sensor was used to determine the concentration of hydrocarbon gases. The edge computing of measurement data was carried out in the ESP8266 microcontroller of the transmission part of the radio line. In order to read digital data from the DHT11 sensor, a library supporting the SDA interface was used. The gas concentration was determined by the voltage at the output of the MQ2 sensor. The built-in 10-bit analog-digital converter of the ESP8266 board was used to get digital measurement data of output voltage. The relative internal resistance of the sensor was calculated based on the measured voltage. This resistance value was used to estimate the gas concentration value based on the calibration characteristics of the sensor. The temperature, humidity, and gas concentration values were sent to the transceiver through the SPI interface. At the receiving end of the radio line, from the output of another transceiver, these values were input to the ESP8266 microcontroller, also via the SPI interface. It is important to emphasize that each of these edge devices at least performed operations of both reading and transmitting measurements of sensors. On the same controller of the receiving end of the radio line, a gateway was created for transmitting gas concentration, humidity, and temperature measurements to the cloud service ThinkSpeak by connecting to a Wi-Fi access point. The change in measurements of air quality control sensors at a certain time interval, which was output to the ThinkSpeak, is right now shown on the screen. Often, there is a need to organize a gateway for access to the global internet network several kilometers away from the sensor network. In this case, the LoRaWAN network protocol can be used for data transmission. This protocol has low energy consumption and uses LoRa broadband modulation at the physical level. The calculation of the range of LoRa radio line is carried out for the real sensitivity values of the RFM95W receiver. The use of the Okamura-Hata radio wave propagation model is proposed in order to estimate the total signal loss in the LoRa radio line. Typical values of LoRa modem parameters for the frequency of 868 MHz are given in Table 1 and right now shown on the screen. The result of calculation of the communication range and data transmission speed on the LoRa radio line for the value of coding rate 4/5 are shown right now in the Table 2. As can be seen from Table 2, increasing the value of the spread factor of the radio signal, SF, leads to increase in the communication range with a simultaneous decrease in the information rate of data transmission. The obtained values of the radio line range make it possible to more accurately determine the wireless sensor network's coverage area when using the LoRaWAN communication protocol. Right now, we live in the era of wireless technologies and AI is evolving rapidly. Today, it is important to keep abreast, to track trends, learn new things, and adopt practices. Thus, we wanted to share with you the results of our work, which showed the possible options for wireless data transmission during the implementation of both short and long-range IoT projects. The range of sensor data transmission between microcontrollers was practically determined for each proposed option. The air quality control project showed the essence of edge computing with combined use of digital and analog sensors. The data transmission of the air quality control system was carried out through a gateway to the IoT cloud service ThinkSpeak. This service made it possible to graphically display measurements that you were actually able to observe today. Thank you for your time and attention.
Thank you. Thank you for your report. And who have a question? Nadia Nikolaevna.
Okay, I have a question. Thank you very much for your report. What's the minimal function of an edge device?
Thank you for your question. I'll try to make it short, not to take a lot of time. So basically, the edge device is a miniature computing device to which sensors or actuators and means of communication are connected. Therefore, it performs applied actions of collecting information from sensors and controlling actuators using means of communication, if it's basically a short explanation.
Okay, thank you. I have a last question for you. Okay, what is the main purpose to the LoRa physical interface?
Oh, thank you. That is a good question. I think it's actually very important to emphasize that the LoRa physical interface transfer speed is like super low. Basically, right now you can imagine it's around like 32 kilobits per second. So that's why the LoRa interface basically is used to transmit data at a very low speed in the IoT projects. So for example, you can use it like for transmitting measurement data from sensors or like controlling remote objects. So you cannot basically transfer like images, videos, I don't know, anything. Well, theoretically you can, but it will take hours or even days to transfer. So that's why it's only used for small amounts of data.
Okay, thank you for your answers. Maybe one question. Okay, after Sergei Semerikov. Sergei Alexeyevich, please.
Nikolaevna, I'm sorry. You should be not fast.
My last question.
Zero. No, so it's right. Not about video transmission through this. LoRaWAN adaptively changes the data rate and transmitter power for each edge device individually to ensure reliable data packet delivery. How this adaptive mechanism works in practical implementation, and what is impact on network performance and energy efficiency?
I'm sorry, can you please repeat the very last part and something efficiency? I didn't really understood that one, please.
I'm sorry. Could you elaborate and how this adaptive mechanism changes the data rate and transmitted power for each edge device individually? How this adaptive mechanism works in practical implementation? And how it impacts on network performance and energy efficiency? Or
Okay,
it seems the future prospects of your research.
Okay, thank you for your question. Yes, you are absolutely right. It adaptively changes, which is actually a good thing, because it can actually transfer like a lot of packets. And oh, I forgot, I'm sorry. Okay, so maybe I will not answer the question you meant, but I'll try to explain something at least. Well, the main purpose of using this protocol or physical LoRa interface is it's for situations when you don't have the access to the internet, basically. So, for example, if you have a sensor in wireless networks, well, let's imagine somewhere in the field, whatever, like somewhere outside the coverage of internet or Ethernet coverage area, you need to transfer somehow this data to the gateway, like let's say this. So you have to receive the data. So this is one of the way you can actually do it because it uses linear frequency modulation. And we actually calculated for a specific transceiver like RFM 95 modem at a given frequency. And at this given frequency, if, for example, there is a spread factor, this is the coefficient that actually determines the data bits quantity transmitted during the time. For example, if you maybe the table was quite quick to disappear from the presentation, but I think it's kind of important that if you actually make the duration of symbol bigger, this speed of signal or this rate actually decreases, but it helps to transfer data on the longer distances. So you lose at the speed at the given power of your transceiver, right? But you can actually make it transfer data for like longer distances. Like our calculation showed that at the given power of the transceiver and frequency, you can reach up to 10 kilometers in data range, and but the speed is actually like low. So I'm sorry.
Thank you for your answer. Really, LoRaWAN is optimal in average. It seems to be a good idea to make much of implementation experiments with in different settings. Thank you very much.
And we have a question from Dmitro Schweika. Dmitro, please. Please turn the microphone.
Yeah, I just have a quick question. I have noticed that you're using ThinkSpeak as a platform to which you are transmitting the data measurements. I'm just interested, do you have any collaboration with them, or it's just a platform that was the most suitable for your use case? I'm just interested if you have any comparison with other platforms to use, or you're just using ThinkSpeak just because it's yeah. So I'm just interested why you're using ThinkSpeak. Thank you.
Thank you, Dmitry, for your question. Well, we were using ThinkSpeak because we just were using it. It was just out there in the internet and it was open and you can just use it for free. No need to have any kind of subscription or something. But I noticed that the other participant of our today's workshop were using Blink, and probably I think it might be even in some situations it might be even better to use Blink because, for example, the problems we faced with ThinkSpeak is that there was a necessary condition for the correct operation of the service in the implementation of delay of at least 20 seconds between the transmission of measurements. We tried to reduce the delay of time or to eliminate it at all, so it would be done simultaneously, but it actually led to a disruption of the service. So that was actually the problem. So maybe if we will be actually implementing something in the future, we might think of implementing it in a different service, because right now the delay of 20 seconds, well, it's not like crucial and it's not like super big problem, because if we're talking about indoor service like home station or whatever, there was, in my opinion, there is no need to measure every 10 seconds the air quality system or like, I don't know, anything else, probably, I guess. If like in 30 seconds, pretty much nothing would change and it won't cause any problems. Probably, maybe I'm missing something, but well, generally speaking, but maybe we should try another service if we're gonna do. But right now, basically, probably more we are into LoRa and LoRaWAN networks. So who knows? Maybe in
Yeah, I just asked this question because I know that like in the Things board we also have LoRaWAN integrations, and I'm just maybe wanted to say if you want, you can try Things boards also. It's also open source, and I think it will be nice to have some collaboration, and we will be glad to work with another like Ukrainian scientists and developers. So just in case.
That's great. Thank you. Thank you. I actually wrote down this things board and we will actually look at it because honestly, personally, I never heard of it before like today. So that would be actually interesting thing to know. Well, as I said, like in my presentation, it's actually very important to share and to learn new things from other people, from the internet, and well, just to use any opportunity you can. Because as was said in the beginning, like, yes, we try to probably invent bicycle, but I would call it a prototype, because basically we'll learn in something. We'll learn on something that already probably exists and just try to improve, try to add something new. So yes, thank you so much for this information. That's actually very useful.
Okay, so thank you for your answers, and now we invite the next actor to the speak is Irina Bespalko and Leonid Naumchuk, and an analysis of approach to the future of satellite classification determined based on modeling of linguistic variables and membership functions. And I share video.
For your attention to presentation on the topic and analysis of approach to the features of satellites classification determining based on modeling of linguistic variables and membership functions. The composition of the space systems of the world's leading states that carry out space activities is actively changing today. The number of satellites is increasing, their functional capabilities are improving due to the development of the material technical and scientific base. Considering the martial law introduced in Ukraine from February 24, 2022, space support, and in particular, space situational awareness, space situation analysis is an urgent need in the process of planning the activities of national security and defense entities, which requires a clear classification of satellites, which is determined by their purpose. A clear understanding of the purpose of satellites allows you to take into account the peculiarities of their functioning and influence on various spheres of activity of state authorities, especially to ensure the national security and defense of Ukraine. It is necessary to classify satellites, which is an important task for carrying out space activities, for example, planning, observations, protection against possible observations from space, etc. The development of technologies and the appearance of new satellites may require the expansion of existing classification features, that is, such as the satellites classes defined for a certain period of time which are not static. Under such conditions, classification features obtained from both a priori, a posteriori information about satellites can be numerical, categorical, or linguistic, taking into account heterogeneous features requires the use of appropriate mathematical apparatus which will allow them to be formalized for the further classification of satellites, which is a current scientific task. The problem of data classification can be solved by the fuzzy inference system, which is based on the algorithm of obtaining fuzzy conclusions based on fuzzy premises using concepts of fuzzy logic. The process of fuzzy derivation combines the main concepts of fuzzy set theory, membership functions, linguistic variables, fuzzy logical operations, methods of fuzzy implication, and fuzzy composition. The main stages of fuzzy derivation are fuzzification of input variables, aggregation of preconditions and fuzzy rules, activation or composition of subconclusions and fuzzy rules, accumulation of conclusions of fuzzy rules. Consider the first stage of the process of fuzzy derivation, fuzzification of input. Variables establishing correspondence between the specific, usually numerical, value of a separate input variable of the system of fuzzy derivation and the value of the membership function of the corresponding term of the input. Linguistic variable. After that, specific values of membership functions for each of the linguistic terms used in the prerequisites of the fuzzy inference. System rule base must be determined for all input variables. Formally, the fuzzification procedure is performed as follows. At the beginning of fuzzification, the specific values of all input variables of the fuzzy inference system are determined, that is, the set of values. Next, we consider each of the subconditions of the form of the fuzzy derivation. System rules, where T is some term with the corresponding membership function. X, which can be analytically specified. At the same time, the value is used as an argument of X in the quantitative. Value is found, which is a result of fuzzification of the subcondition. The Experimental results were obtained using an example, the launch of the Viasat 3.2 satellite, Viasat 3 EMEA, is planned for 2024. Correspondence between the linguistic variable and its values is given in the tables. For example, consider them. Features Beta 1, type of launch vehicle in Beta 2, type of orbit, which are indirect linguistic. A priori, features for further classification of the satellites. The results of classification for the input linguistic variable Beta 1 and linguistic variable Beta 2 are given in the on-the figure S. Thus, using the theory of fuzzy sets, the linguistic variables of some features of the satellite's classification were formalized, and an example of the calculation of their membership functions was given. The following steps in the classification process are given in the slide. The proposed approach can be used to solve the problem of complex classification of satellites, taking into account the majority of heterogeneous features. Thank you for your attention.
Thank you for your report. And who won't ask the questions? Dmitro Shvaika, please. Maybe Dmitro don't. Yes. Sergey Alexeyevich, please.
Yeah, excuse me. So I raised the hand for the first previous time, and it's still raised. I'm not sure why. Let me try to clear that. Yes, sorry.
Sergey Alexeyevich, please.
Thank you. Cats always propose to raise hand in any inconsistent situation. Oh, yes, thank you. The most interesting part of this presentation was the 6th and 7th slides. I see the falsification process for input variables is quite unordinal, absolutely unordinal. You use such variables as a type of launch vehicle and a type of orbit, and your functions are very complex. Could you explain how variations of your variables can be accounted for in the fuzzy inference system, especially when dealing with real-world data that may not always fit neatly into predefined linguistic terms. And can you give some additional detail on constructing of your functions. Thank you.
Irina, we don't hear you.
It seems to be Irina can some technical issues. It's possible variant to make your answer in the chat.
Communication.
Maybe we're waiting the answer in the chat. Yes, and.
I will try to duplicate my questions in the chat, and Irina can answer when when she can.
Okay, let's go the next. Irina, please wait 1 minute.
Irina
Asked.
Okay, maybe next cases.
Okay, yes, maybe we invite the next out to the speak is Andrei Yarmilko, Irina Razumi, and Sergei Naumenko, and article Data Security of IoT Devices with Limited Resources, Challenges and Potential Solutions. And I share the screen.
Let's present a research data security of IoT devices with limited resources, challenges and potential solutions by authors Irina Razumi, Andrei Yarmilko, and Sergei Naumenko. Embedded Internet of Things devices are compact, integrated devices embedded in various objects capable of collection, processing, and utilizing data, as well as exchanging it over a network without direct human involvement. However, the security of embedded IoT devices has become a key issue limitation their application. This problem arises from the imbalance between the potentially high functionality of such devices and their resource constraints. The architecture of embedded IoT devices is presented as the interaction of three main components. First component, sensors and actuators, components that provide data collection and transmission. Sensors gather information from the environment, temperature, humidity, etc., while actors perform corresponding actions during devices on-off. Second, data processor is responsible for processing and analyzing the collected data. This can be a microcontroller or a specialized computer systems. And the last one, network interface facilitates communication with the external environment through various network protocols such as Wi-Fi, Bluetooth, LoRa, Zigbee, etc. The primary functions of embedded IoT devices include data collection, obtaining information from sensors, data processing, analyzing and processing the acquired data to perform defined tasks, and actuator control, sending signals to actuators to execute specific actions. The typical properties of embedded IoT devices are accompanied by limitations that encompass the following aspects. First, computationally power embedded IoT devices have limited capability of complex computation due to restricted computational power. This may lead to constraints in applying advanced encryption algorithms and performing computationally-intensive operations, reducing the device's security level. Second, memory. The limited memory capacity in embedded devices complexities the storage of a large amount of data and software. This may result in reduction of available resources for storing encryption keys, user data, and other critical elements, increasing vulnerability to attacks. The last one, power supply. Embedded IoT devices are often powered by anonymous energy sources or have limited power consumption. This limitation in power supply can lead to unforeseen interruptions in device operation or limit security capabilities. These limitations impact the capabilities of embedded devices in implementing robust security measures and pose a challenge in ensuring data reliability and protection. One of the key issues in the field of embedded IoT devices is the presence of vulnerabilities that can be exploited for attacks and security breaches. Integrate authentication and authorization. A lower level of authentication can serve as a starting point for unauthorized access to the device. The absence of robust user identity verification methods, the use of weak passwords, or simple authorization method can be entry points for cyber attacks. Second one, insufficient cryptographic protection. The use of weak or outdated encryption algorithms in IO devices makes the data more vulnerable to interception and compromises. If encryption employs keys of influence, links of vulnerable to unknown attacks. And the last one, insufficient software updates. Limited memory in embedded devices can complicate the software update process. This could create a risk of temporary or permanent vulnerability of the device to new threats of vulnerabilities. Examining memory, energy consumption, and computational power, we can determine that memory limitation in embedded devices can lead to buffer overflows and constraint in strong encryption keys, complications the cryptographic protection of information. Energy supply is a fundamental factor limiting the operational duration of devices and the risk of potential DOS attacks due to targeted expenditure of limited energy. Limited computational power complicates the application of complex encryption algorithms and may contribute to the execution of malicious code in case of influencer input data validation. The discussed limitation expose risks that need to be carefully considered and adequately addressed in embedded I/O devices to ensure the reliability, confidentiality, integrity of the processor's data. Risks arisen from memory limitation. Energy consumption of embedded system may be influenced for the operation of cryptographic protection, both due to the design features of anonymous I/O model and intentional and unauthorized impact on their power components. Threats related to energy consumption pose a wide range of security risks for the system. This slide shows table which presents impact of embedded device resource constraints on information security. This analysis shows memory, battery charge, and energy consumption constraints significantly influence the cryptographic protection of information in I/O devices. Memory limitation often impacts the device's ability to store encryption keys and other essential data, increasing the risk of unauthorized access and information leakage. Meanwhile, battery charge limitation may lead in unauthorized disruption in the device's operation, reducing its reliability and the efficiency of protective mechanism. Finally, limited energy consumption can restrict the application of resource-intensive protective algorithms, particularly in the field of cryptographic security. Each of these aspects requires detailed consideration and analysis to ensure effective and adequate protection for embedded I/O devices. This diagram is presented on this slide describes the degree of impact of memory constraints on key storage, security management, and system vulnerabilities. Memory constraints in I/O devices can pose a significant risk to data security. On one hand, limited memory can complicate the storage of large amounts of data or complex software algorithms necessary for effective cryptographic protection. On the other hand, influencer memory can reduce the efficiency of key management, which is critically important for ensuring the security of communication processes. Memory limitation in our devices can lead in indicative storage and management of encryption keys, increasing vulnerability to attacks. Battery charge limitation in I/O devices can cause disruption in the operation, especially in critical situations. This may lead to failure to perform essential security operation and authorize access to data. Additionally, a low battery charge can limit the efficiency of encryption and other protection mechanisms. The diagram is presented on this slide illustrates the impact of battery charge limitations on the activity of security protocols, the risk of data loss, and constraints of protective mechanisms. The diagram shows that battery charge limitations have the most significant impact on the risk of data loss during interruption in operation. This underscores the importance of developing energy-efficient solutions to ensure the reliability and continuity of security functions. Limitation on energy consumption in I/O devices can be an obstacle to using resource-intensive security algorithms, especially in the field of cryptographic protection. This may lead to the selection of less powerful and therefore less security encryption algorithms. Additionally, limited energy can slow down the processes of detection and responding to potential cyber threats. The difficulty of using complex cryptographic algorithms in I/O devices makes them vulnerable to advanced cyber attacks. The diagram is presented on the slides illustrates the impact of energy consumption constraint on the security of I/O devices. The diagram shows that limited energy consumption most significantly affects the selection and effects of security algorithms. This emphasizes the need for the development of energy-efficient cryptographic solutions that can provide the double level of security with constrained energy consumption. The percentage on all diagrams reflects estimated conclusion derived from expert opinions in this field. By focusing on key aspects of such limitations, such as memory, battery charge, and energy consumption, effective strategies can be developed to enhance the security level of I/O systems. Lightweight cryptographic algorithms. Development and use of cryptographic algorithms that require minimal resources for execution but still provide reliable data protection. Efficient energy management algorithms. Implementation of algorithms that optimize energy consumption without compromising security can ensure longer device runtime and security system reliability. And memory optimization. Development of methods for effective utilization of limited memory space, including compact storage of encryption keys and using memory for security functions. Adaptive security mechanism. Creation of security systems capable of adapting to changes resource constraints to maintain an optimal level of protection in different operation conditions. Improvement of authorization algorithms, implementation of effective authorization algorithms that provide a high level of security with limited complete resources. And the last one, security communication protocols. Development of specialized communication protocols for I/O that are optimized for efficient resource utilization and ensure reliable data protection. These strategies form the foundation for ensuring the security of I/O devices operation in resource-constrained environments. In the context of ensuring security for I/O devices with limited resources, it's important to recognize that effective security requires a multidimensional approach. This approach should involve the integration of technical innovations and strategic planning. Considering the constraints in memory power consumption and computer power, the development of lightweight cryptographic algorithms that utilize minimal resources becomes a priority to ensure reliable data protection. Security systems should be flexible, adaptive, and capable of maintaining a high level of security despite resource limitations. This includes not only technical aspects but also operation resource management, especially concerning energy and memory. Thank you for your attention.
Okay, thank you for your report. And who have a question?
May I?
Yes.
Thank you very much for your presentation. My question. What is the main security problem of the Ethernet of Things edge device you see today?
The main problem was to implement new encryption algorithm with speed and low power attention. So for now, it's hard to us to implement this because everything what we tried, it's necessary a lot of performance and in this case also a lot of power. So it's hard to use less memory and also use less power. So just currently working on this.
Thank you.
Okay, who have any question? Okay, if we no questions, thank you for your answer. And sorry. And I would like tell something. In a four-stage computing workshop, a total of 27 participants took part, including in a circle from Netherlands, 1 person, Singboard, USA, 2 person, Technical University of Ukraine, Igor Sikorsky, Kiev Polytechnic Institute, 1 person, National University Zaporizhia Polytechnic, 1 person, Pukhov Institute for Modeling and Energy Engineering of North of Ukraine, 1 person, the National University of Life and Environment Science of Ukraine, 2 person, Alexander Dovzhenko Glukhin, National Pedagogical University, 3 person, Korolev Zhytomyr Military Institute, 4 person, Bogdan Khmelnytsky National University of Cherkasy, 4 person, and Zhytomyr Polytechnic State University, 8 person. Now we invite all authors who presented their materials today to submit a 30% expanded version of the article for publication in the new Journal of Edge Computing. All requests for such articles will be sent to authors after 10 April. We now ask everyone to turn on their cameras for group photography. Please turn the cameras. And we please розверніть, будь ласка, вас на екранчику. Please turn the right your cameras. Oh, okay.
Машина ручками.
Our cameras, your cheeses.
Можно скриншотиком зробити? Принскрином.
Так, чизи срочно чизи.
Окей, я думаю, що можна, Сергій Олексійович, завершити українською мовою, так? Ми гарно провели семінар англійською мовою, так, нашою рідною, каже Сергій Олексійович, нашою рідною англійською мовою. Всім щиро дякую за участь в нашому семінарі, запрошуємо до наших подальших семінарів і конференцій. Ось наступні наші конференції вже відбудуться у травні, так, Сергій Олексійович, у нас там дуже багато поданих матеріалів, які нам треба теж заслухати. Ось, і відповідно з усіма обговорити. Всіх запрошуємо до розширених версій статей в нашому журналі. Журнал з лютого місяця є фаховим і безкоштовним. Після 10 квітня ми розійшлимо всім офіційні запрошення, де буде вказано відповідно вимоги, що треба зробити, як зробити і куди подати. Ще раз всім дякуємо, дякуємо всім за плідну дискусію і запрошуємо до подальших наших семінарів. Всім дякуємо, мирного неба.
Здоров'я, наснаги, хай згинуть наші вороги і слава Україні!
Героям слава! Всім дякуємо, будьте здорові!
Живіть багато.
До побачення.
На все добре, до побачення.
Сергій Олексійович, я стоп надо, да, нажать?
Ліфом, там, червоно внизу.
Ні,